Date on the implementation of the Chrysler Technical Training Skill Core Curriculum. By now, dealerships should have received a brochure that explains the elements of this new system for providing technical training. A short segment at the beginning of the April MasterTech program also provided a general description of the new system. If you saw that segment, you'll recall that the new system provides logical training sequences that progress through a series of levels, and that the course catalog is being updated to make it easy to select courses to suit your needs. If you've read the brochure, you'll also know that another element of the new system, which was rolled out last summer, is convenient online registration for classes through a dealership's dial network. In addition to the brochure, dealerships should also now be receiving the new course catalogs. The catalogs contain all the information you need to clearly understand the nature and benefits of each course, as well as where each course fits into the overall training picture. Dealerships should also be receiving wall charts that display all of the skill categories and the subjects that they cover. You should now be receiving personal training records. These records incorporate any training taken in the last 5 years that can be applied to the new curriculum. Technicians will also receive training passport stickers that are placed in the passport when they take classes at the training centers. These stickers list all of the courses that are available in each skill category. As you begin to use the new core curriculum system, you'll find that it's easier than ever to take the right class at the right time, and that can yield real benefits in your productivity, job satisfaction, and customer satisfaction. Now stay tuned for this month's MasterTech release about the leak detection pump. When you see something like this coming out of a tailpipe, you can tell without a doubt that it's contributing to the already serious problem of air pollution. But did you know that invisible vapors from this car's fuel system could be just as guilty? That's right, you may not be able to see the pollutants, but they could be there. Unless fuel system vapors are captured and routed to the engine, they can become hydrocarbon emissions in the atmosphere. Besides being pollutants in themselves, hydrocarbons combine with other chemicals to form smog and low-altitude ozone. As you may recall from the April MasterTech program on fuel basics, hydrocarbons are compounds of hydrogen and carbon and are present in all petroleum products. Hydrocarbon emissions are the result of unburned fuel in exhaust gas or fuel vapors that have escaped into the atmosphere. Over the years, automakers have been able to drastically reduce the amount of hydrocarbon emissions from vehicles, including those that result from fuel vapors. The purpose of the evaporative control system is to prevent the escape of these fuel vapors from the fuel system. But the smallest of leaks in the evaporative system could allow fuel vapors to be emitted into the atmosphere. And since air pollution is a great concern, there are now new ways to ensure cleaner vehicles. Recent government regulations require that automotive manufacturers meet more stringent OBD2 guidelines concerning evaporative system integrity and functioning. The stricter federal EVAP plan currently being phased in now affects over 40% of Chrysler vehicles and is expected to be incorporated into all Chrysler vehicles by the year 1999. One of the requirements of the stricter regulations is the detection of leaks in the evaporative control system by the onboard engine controller, or PCM. There are two methods of EVAP leak detection used by the automotive industry: vacuum decay and flow. Chrysler uses the flow method because it's more robust and less affected by vapor generation and variations in fuel level than the vacuum decay method. The flow method involves the use of a leak detection pump, which is the device that the PCM uses to monitor the EVAP system for leaks and pinched lines or hoses. According to the stricter EVAP regulations, the monitor must be able to detect leakage as small as a 40,000th of an inch diameter hole. Welcome to MasterTech. This month we're going to take a look at the evaporative control systems used on some Chrysler vehicles, specifically vehicles that use the leak detection pump, or LDP. We'll look at the basic evaporative control system and what has been added to it to make up the leak detection pump monitor. After that, we'll talk about the leak detection pump components and system operation. Finally, we'll show you how to diagnose a system with an evaporative system leak and how to find the leak. The basic evaporative control systems on all Chrysler vehicles are similar in configuration and operation. Components that make up the evaporative control system include a rollover valve located on the fuel tank. This valve prevents fuel from flowing through the fuel tank vent hoses in the event of a vehicle rollover. In normal operation, a vent port in the valve allows the vapors generated in the tank to flow into the EVAP purge canister. Here, the canister vapors are absorbed on activated carbon granules and stored temporarily until the EVAP purge solenoid can route them to the engine to be burned. With input from the PCM, the duty cycle EVAP purge solenoid connects the canister to manifold vacuum when the catalyst is up to operating temperature. During closed throttle, the PCM energizes the purge solenoid 5 times per second. During open throttle, the PCM energizes the purge solenoid 10 times per second. The PCM changes the duty cycle, increasing it for more purge flow and decreasing it for less purge flow. From the duty cycle purge solenoid, vapors are drawn into the intake manifold and then routed into the cylinders. One component you rarely think of when dealing with the evaporative system is the fuel tank filler tube cap. All Chrysler vehicles use a pressure vacuum filler tube cap. The cap has pressure and vacuum valves that only open when abnormal pressure or vacuum is present. The cap is not normally vented to atmosphere. Under normal conditions, the cap seal prevents the loss of vapors from the fuel tank. Be sure to advise customers that it's important that the cap is tightened upon installation. A loose or missing fuel cap could allow vapors to escape, and on vehicles with a leak detection pump, this could trigger a trouble code and cause the malfunction indicator lamp to light. Also, if replacing the fuel cap, be sure the cap with the correct part number is used. Everything that we've looked at so far is basic equipment on all Chrysler gasoline-fueled vehicles. Vehicles that are equipped with stricter EVAP control add a leak detection system and PCM functions, except 1996 and 1997 Grand Cherokees. The leak detection system consists of a service port, a service vacuum supply tee, and the leak detection pump. The service port is used when diagnosing the EVAP system and is the result of the Low Emissions Partnership Consortium, or LEP, in that it is universal on all Chrysler, Ford, and General Motors vehicles. The Service Vacuum Supply Tee, or SVST, is a vacuum tee with 2 check valves. The purpose of the SVST is for applying vacuum from an external source to the LDP solenoid during diagnosis. The leak detection pump is used by the PCM to pressurize the system to allow a leak test to be run. Besides running the LDP monitor, the PCM also conducts a stricter EVAP purge flow monitor, which we'll cover later on. Currently, you'll find the stricter EVAP monitoring system on the Talon, Avenger, and Sebring. Minivans with 3.0, 3.3, or 3.8-liter engines, and on the Cirrus, Stratus, and Breeze, except those having 2.0-liter engines with an automatic transmission. In addition, Sebring convertibles sold in California, New York, and Massachusetts will also have the stricter EVAP monitoring system. For more information about vehicles equipped with the LDP monitoring system and those getting it in the future, refer to this month's reference book. In a minute, we'll take a closer look at the leak detection pump components and operation. But first, try to answer this review question. Which of the following 2 methods of leak detection does Chrysler use for EVAP leak detection? A, flow, or B, vacuum decay? The correct answer is A. Chrysler uses the flow method of leak detection because it's more robust and less affected by vapor generation and variations in fuel level than the vacuum decay method. Now that we've taken a general look at the evaporative control system, let's look at what has been added to it for the LDP monitor, starting with the leak detection pump and its components. The PCM uses the leak detection pump solenoid to operate the system. The solenoid accomplishes this by connecting the pump to vacuum and to atmosphere. When the LDP solenoid is energized, manifold vacuum in the pump cavity draws the diaphragm up. When it is de-energized, the pump cavity is connected to atmosphere, and spring pressure forces the diaphragm down. With signals from the PCM, the LDP solenoid causes the EVAP system to seal and pressurize so the PCM can monitor it. To seal the system, the leak detection pump uses the canister vent seal valve. The rod this valve is attached to is held down by the pump diaphragm, keeping the valve open. When the solenoid first connects the pump to vacuum, the diaphragm moves up against pressure from the diaphragm spring. As the diaphragm is retracted and no longer in a position to hold down the vent seal valve, a spring on the valve pushes the valve up to seal off the passage between the remote filter and the canister. Once this passage is sealed off, to pressurize the system, the diaphragm moves up farther, drawing air into the pump through the remote filter. Then the diaphragm moves down part way to force it out of the pump into the EVAP canister, and from there into the fuel tank. When the system is sealed, one-way check valves in the pump allow the air to flow into and out of the pump. As the diaphragm moves up, air is drawn in through the inlet check valve, and the outlet check valve is forced shut. Likewise, when the diaphragm is pushed down, air is sent through the outlet check valve into the purge canister, while the inlet check valve is forced shut. The spring on the diaphragm is calibrated so the system can achieve an equalized pressure of 7.5 inches of water, or about 1/4 of a psi. When a pressure of about 7.5 inches of water builds up in the pumping chamber, it equals the force of the pump diaphragm spring, and the pump diaphragm will no longer move. A reed switch located on top of the leak detection pump is used by the PCM to detect lack of diaphragm movement, thus checking the system for leaks. Now we're ready to look at how the PCM uses the leak detection pump to monitor the EVAP system. But before we do, let's have another review question. Which of the following components actually performs the sealing of the evaporative system? A, the reed switch. B, the check valves. Or C, the canister vent seal valve. The correct answer is C. To seal the evaporative system, the leak detection pump uses the canister vent seal valve, which is normally held open by the spring-loaded diaphragm on the vacuum-driven pump. The main function of the leak detection pump is to pressurize the evaporative system so the PCM can monitor the pump cycle time through the action of the reed switch. The PCM determines if there is a leak in the system based on the length of time it takes to cycle the pump. As mentioned earlier, the leak detection pump relies on input from the PCM for its operation. But in order for the pump to operate, some enabling conditions must be met first. The PCM checks the outside ambient temperature, which must be between 40 and 90 degrees Fahrenheit. The coolant temperature, which must be within 10 degrees Fahrenheit of the outside ambient temperature. And the fuel level, which must be between 15 and 85% of fuel tank capacity. Also, the PCM checks to make sure there is no residual pressure in the system at key on. If any of these conditions are not met, the leak detection test won't run. For specific monitor enabling conditions, refer to the DRB3 onboard diagnostics help screens. Since seasonal temperatures might prevent the pump from operating for long periods of time, even if the ambient temperatures prevent the test from being run, the PCM will still cycle the pump once at every key on to exercise it. If all the enabling conditions are met, the system will continue on to pump initialization. First, the PCM will energize the LDP solenoid to check the integrity of the pump reed switch. The intake manifold supplies vacuum to the pump, pulling the pump diaphragm up. The PCM then checks to make sure the reed switch opens. If all these conditions are met, the PCM begins the monitor by first cycling the pump to determine if there is a blockage somewhere in the system. If a rapid buildup of pressure causes the pump to stop cycling, the PCM assumes there is a pinched line or obstruction between the fuel tank and the leak detection pump. It will still, however, attempt to check for leaks and check purge flow. Before the PCM will store a one-trip failure for the pinched line, the LDP monitor and purge flow test must both be run. The next step in monitoring by the PCM is EVAP system testing. During testing, the leak detection pump is controlled in two modes, pump mode and test mode. In the pump mode, the on and off periods of the pump are cycled at a fixed rate to attain a rapid pressure build, resulting in a shorter overall test time. In the test mode, only the on period is cycled at a fixed rate. To check for leaks, the PCM measures the LDP cycle time, which is the time from when the solenoid is off until the reed switch opens again. Now let's take a closer look at the leak detection pump test sequence. In the pump mode, the LDP solenoid and pump diaphragm cycle to pressurize the evaporative system. At this point, the PCM determines how long the pump must run in the pump mode. Again, fuel level is an influence. Based on the amount of fuel in the fuel tank, the PCM can determine vapor volume, thus determining how long it will take to pressurize the system. For example, it would take longer to pressurize a system with low fuel level and high vapor volume than it would a system with high fuel level and low vapor volume, due to the larger amount of space available in the system. Sometimes the pump will need to run longer than the time period set by the PCM to pressurize the system. In this case, it will enter a low pressure check mode, meaning it will loop back and run in the pump mode again. This could occur several times until the system is pressurized, and is more likely to occur on vehicles with low fuel levels as it takes longer to pressurize the system. Once a pressure buildup occurs, the PCM switches the pump from pump mode to test mode to determine whether or not the system has a leak. If no leak is present, the pump runs until pressure is equalized and the pump diaphragm will no longer move. This is communicated to the PCM when the reed switch no longer closes. If a leak as small as 40 thousandths of an inch in diameter is present, the pump cycle time from solenoid off until switch closure will decrease until it is at a rate proportional to the size of the leak. The smaller the leak, the smaller the cycle rate, and the larger the leak, the larger the cycle rate. So not only can the PCM determine whether there is a leak in the system by monitoring the cycle rate of the pump, the PCM can also calculate the size of the leak. If a leak is discovered, a one-trip failure and freeze frame data will be stored. The test will discontinue at the end of the mode, and no further checks will be run. The leak detection check is a two-trip monitor, meaning if this malfunction occurs for 2 consecutive monitor cycles, the PCM will store a trouble code in its memory and cause the malfunction indicator lamp to illuminate. If no leak was detected, the leak test is completed and the purge system is activated to depressurize the system. Now that the leak check part of the diagnosis is complete, the pump diaphragm will return to the full travel position, and thus the canister vent valve will unseal the system. After the LDP monitor is run, the evaporative system operation is checked using the purge flow monitor that I mentioned earlier. Once per key cycle at either the first or second closed throttle, the PCM will run the purge flow monitor under the following conditions. When vehicles with an automatic transmission are in gear at idle, or when vehicles with a manual transmission are in neutral at idle, the PCM will first update purge-free adaptive memory cells and then move on to stage 1. It's important to keep in mind, though, that if you unplug the PCM's connectors or reset adaptive cells, you must update the cells, or this purge monitor will not run. In stage 1, the PCM compares purge-free idle cells to purge normal cells. If there is a large adaptive difference, the PCM infers purge flow, passes the system, and all operation is stopped. If there is not a great enough difference, the PCM moves on to stage 2. In stage 2, the PCM will energize the LDP solenoid to seal the system, and then increase the purge duty cycle. It will continue to increase purge duty cycle until either the RPM rises by a predetermined amount, the short-term adaptive memory changes by a predetermined amount, or the idle air control closes by a predetermined amount. If these don't happen, the PCM will set a one-trip fault. As you can see, the leak detection system is quite complicated. So let's check your understanding of it before we go on to EVAP system diagnosis. Which of the following is not considered by the PCM before it enables leak detection pump operation? A, coolant temperature, B, open throttle, or C, fuel level? The correct answer is B. Before the leak detection pump can operate, the PCM checks the outside ambient temperature, which must be between 40 and 90 degrees Fahrenheit, the coolant temperature, which must be within 10 degrees Fahrenheit of the outside ambient temperature, and the fuel level, which must be between 15 and 85% of fuel tank capacity. Also, the PCM checks to make sure there is no residual pressure in the system at key on. Now that we've seen the leak detection pump components and how they operate, in this segment we're going to show you how to diagnose an EVAP system with a large or small leak, and how to find the leak. In both situations, the vehicle was probably brought into the dealership with the mill illuminated after failing the monitor on 2 trips. So first we connect the DRB3 to the data link connector and check for existing trouble codes. As you can see, the DRB3 indicates that there is a large EVAP system leak. Remember I said earlier that a loose or missing fuel cap can trigger a trouble code. So before proceeding, make sure it is tightened properly. To check for the leak, we'll need to apply pressure to the evaporative system. To reduce the pressure build time, you may want to make sure the fuel tank is about 50% full. To pressurize the evaporative system, we'll use Miller Special Tool number 6872A, the evaporative system pressure pump. With the key on and the engine off, install an external source of continuous vacuum of at least 5 inches of mercury to the SVST. Using the DRB3, select Engine from the Select System menu. Once we're in Engine, the Select Functions menu will appear. And from the Select Functions menu, we'll select System Test. This will take us to the Engine Systems Tests menu, at which point we'll select Leak Detection Pump Test. This will bring up an information screen, which describes what we need to do to test the system. After reading this information, we'll want to press Enter to move on to the next screen, the Leak Detection Pump Test screen. And here we'll select Option 3, Hold PSI. At this point, the DRB3 directs the PCM to energize the LDP solenoid, which allows the vacuum from the SVST to pull up the pump diaphragm and close the vent valve seal. Connect the evaporative system pressure pump supply hose from Miller Special Tool number 6872A to the leak detection pump service port. Connect the positive cable of the tool to the battery's positive terminal, and connect the negative cable to the battery's negative terminal. Then set the pressure hold valve to the open position and the vent valve to the closed position. Before we continue, keep in mind that after the system is pressurized, opening the vent valve of the pressure pump releases the system of this pressure, which is in the form of fuel vapors. It's important that you keep lighted cigarettes, sparks, or any type of flame away from the area while performing this procedure. Now we're ready to pressurize the system. turn the pump timer on. If the EVAP system leak is large, as you can see, the pump may not be able to fully pressurize the system. You'll see this as the pump continuously running. If this is the case, and you can smell fuel vapors, the leak is probably located between the passenger compartment and the fuel tank. If you don't smell fuel vapors, the leak is more likely in the area of the engine compartment. In our case, the cause is obvious: a disconnected hose on the vapor line. The procedure for checking for a small leak is similar. Again, using the DRB3, select Engine from the Select System menu. In the Select Function menu, select System Test. This will take us to the Engine Systems Test menu, at which point we'll select Leak Detection Pump Test, which again brings up the information screen. Press Enter to move to the next screen, the Leak Detection Pump Test screen. As before, with the key on and the engine off, install an external source of continuous vacuum of at least 5 inches of mercury to the SVST, and select option 3, hold PSI from the Leak Detection Pump Test screen. Again, the DRB3 directs the PCM to energize the LDP solenoid, which, as you'll recall, allows vacuum from the SVST to pull up the pump diaphragm and close the vent valve seal. Now connect Miller's Special Tool number 6872A to the leak detection pump service port. With the pressure hold valve in the open position and the vent valve in the closed position, turn the pump timer on to pressurize the system. As you can see, in the event of a small leak, the pump cannot fully pressurize the system. Finding a small leak is a little more difficult than finding a large leak. To do this, we'll use the Paradise 300 ultrasonic leak detector to listen for leaks. Connect the leak detector hose to the port on top of the Paradise 300. Then connect the headphones and turn the power on. Since we're applying pressure to the system in order to listen for the leaks, it's a good idea to isolate the pressure pump from the vehicle as much as possible, and put the vehicle on a hoist. Now we're ready to begin. We'll want to start at the rear of the vehicle and work our way forward. Using the ultrasonic leak detector, start at the gas cap. Then check the fuel fill and vent hoses. Next, check the fuel tank rollover valve. And following the fuel and vapor lines, work your way to the front of the vehicle. Check the EVAP purge solenoid, canister, and leak detection pump. If a leak is present, you should be able to hear it through the ultrasonic leak detector. If the suspected leak is due to a cracked hose, it could be a little more difficult to hear. In this case, you may want to try the soap suds method. Apply a solution of soap and water to the area of hose with a suspected crack. If a crack is present, the soap solution will bubble up where air is escaping. After your diagnosis and repair, retest the vehicle for leaks using Miller Tool 6872A and the Paradise 300 ultrasonic leak detector or the soap suds method to verify that the repair is successful. Well, that's it for another MasterTech. Be sure to join us next month when we'll be introducing the new Dakota. We'll see you then.